NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hey, good evening, ladies and gentlemen. How's everyone tonight? Good, good. Excellent. Well, thanks for coming out to join us again. The Asteroid Redirect Robotic Mission concept seeks to rendezvous with, capture, and redirect a translunar space, an entire small near-Earth asteroid. It would focus the capabilities of the science, technology, and human exploration communities on a grand challenge, creating a new synergy between robotic and human missions to advance human space exploration beyond low Earth orbit for the first time in 50 years. This talk addresses the key aspects of the concept and the options studied to assess its technical feasibility, including evaluations of the expected number of potential targets, the necessity to adequately characterize candidate targets, the spacecraft design, the process to capture a non-cooperative asteroid in deep space, and the power and propulsion technologies required for such an endeavor. Tonight's guest has worked on numerous spacecraft and technology projects since joining JPL in 1977, including the Galileo mission to Jupiter and the Shuttle Imaging Radar C. He was also responsible for the design, development, test, and launch of the Mars Pathfinder spacecraft that landed successfully on Mars on July 4th, 1997. He was a project manager of the Deep Impact project from formulation through the critical design review in 2002, then worked as the chief engineer of the Mars Science Laboratory until August of 2004, when he was appointed chief engineer of JPL. In February of 2007, he was named NASA's chief architect and program systems engineer for the Constellation program, which included responsibility for the architecture of a new human exploration spaceflight system to the moon and beyond. He returned to JPL as the chief engineer in December 2009 and currently is the pre-project manager for the conceptual design of the cross-agency study of the Asteroid Redirect Robotic Mission. He received his BS in Mechanical Engineering from the University of New Mexico in 1977 and an MS in Aeronautical Engineering from Caltech in 1982. Additionally, he is the recipient of 2 of NASA's Outstanding Leadership Medals for his work on Mars Pathfinder and Constellation. Ladies and gentlemen, please help me welcome tonight's guest, Mr. Brian Muirhead.
So what would you say to somebody who said they were working on a mission to go out into deep space, rendezvous with an asteroid, capture it, bring it back and put it in orbit around the moon? Crazy, exactly right. You think they were crazy. You'd say, that sounds impossible. Well, as all of us here at JPL know, that's what we do at NASA. We love the impossible. And this has got a great flavor of the impossible, and I'm going to share that with you tonight. So the Asteroid Redirect Mission is actually 2 missions. It is a robotic mission, which is the mission that I'm primarily responsible for. It is a cross-agency project team of JPL, Glenn, Langley, Goddard Space Flight Center, as well as Johnson Space Center. And the crewed mission, which is primarily the responsibility of JSC. So I'm going to describe for you tonight the basic elements of this project. But I want to start with what is NASA thinking today in human spaceflight? Well, we're not just thinking about where are we going. We're thinking about how we're going to get there. We're not just thinking, what's the destination? We're thinking about what capabilities do we need? What capabilities are we going to develop that'll become the elements that we can use as we go from low Earth orbit out to Mars? The thing I really love about this picture, and this is one that Bill Gerstenmaier, the director of the Human Space Exploration, or Human Exploration and Operations Directorate, used at a recent Von Braun symposium. It's a picture that shows 2 ARRM robotic spacecraft with additional liquid propulsion carrying a human habitat into orbit around the moon, around Mars. So this is showing what we're thinking about, how ARRM itself has become such an integral part of the human exploration program strategy. So what is ARRM? Well, it's about capturing a whole asteroid, rendezvous with, capturing a whole asteroid, and bringing it back and putting it in orbit around the moon. There's another option we're also looking at, which is going to a large asteroid, hundreds of meters in size, and picking up a boulder that's on the order of 2 to 4 meters, and bringing that and putting that in orbit. For the individual asteroid, we're talking about something that's 10 meters in diameter and as much as 1,000 tons. And by the way, I'm going to do metric tonight because I know all you JPLers understand that. So, and then once we're in orbit around the moon in what we call a distant retrograde orbit, which is a very stable orbit, then the crew will come visit sometime in the 2020s, early 20s, maybe as early as 2023. So let's go into a little bit more detail about why is NASA doing this? What's NASA get out of this? Well, it really addresses a number of very important objectives for the agency. First up, it demonstrates high-power solar electric propulsion. We're talking about solar arrays that can put out 50 kilowatts of power. We're talking about a SEP system that can push, that is using basically is powered with 40 kilowatts of power. Dawn's thrusters are basically powered at about 2.5 kilowatts. So we're talking about a major upgrade in power, but even more importantly, we're talking about a major throughput of propellant. We're talking about using as much as 10 tons of xenon. The Dawn spacecraft is carrying less than 500 kilograms. So we're talking about a major ability to move large mass in the solar system. Like I said, maybe as much as 1,000 tons. Tons, that wasn't kilograms, and that wasn't grams, that was tons. Operation in close proximity to a near-Earth object. In fact, with our option B, we'll actually land on the object and interact with it directly. But either way, we'll be using terrain relative navigation, optical navigation, to control our spacecraft around the asteroid in both cases. We also have the capability to demonstrate some planetary defense techniques. These would be techniques that actually could divert a potentially hazardous asteroid if it was on a track to harm the Earth. These are not necessarily primary techniques, but I'll describe them for you in a little bit more. And then very importantly, this is a target for maybe as early as the second crewed mission of the Space Launch System and Orion. So this is a chance for humans to go back to the moon, in fact, be literally farther in deep space than humans have ever gone before, rendezvous, dock, in fact, with our spacecraft, and perform extravehicular activity to sample our asteroid. And this is in fact a building block for much more. This chart is really important to me because it shows how NASA is changing, it's adopted the Asteroid Redirect Mission as a central part of its strategy. And the strategy starts today with where we are now. Earth, we're what we call Earth reliant. We're in low Earth orbit, the capabilities that we've built using the shuttle and with space station, but that's where we've been since 1981. What we're moving to is what we call the proving ground. This is the region in the cislunar space in which we can now prove out new capabilities. We can develop, put into operation, develop new hardware, test out that hardware, develop new capabilities, test out those capabilities, get experience in working beyond low Earth orbit. And I'll describe a little bit more about the nature of the crewed mission. But with this, basically, ARRM is really literally the first building block in this proving ground upon which we can then extend. Ultimately, from this proving ground, we can move on to Mars. In fact, we've shown that the distant retrograde orbit, which is about 70,000 kilometers above the surface of the moon, is a very good staging area for building up systems that we can then send to Mars. So again, ARRM you see here in orbit around the moon. You can see elements of ARRM going to Mars. In fact, our concepts for extending the ARRM spacecraft from a 50 kilowatt system to a 150 kilowatt system enables us to move large payloads, 40-ton-ish class payloads, to the Mars system, to either put them in orbit ready for humans or maybe put them on Phobos or Deimos for surface missions there. So ARRM is an integral part of the future of human exploration. So ARRM itself is made up of three major elements, and it's actually funded and supported by, it's supported by three major elements at NASA headquarters. Major partner is the Human Exploration and Operations Directorate, led by Bill Gerstenmaier, the Space Technology Mission Directorate, led by Mike Gazarek, and supported by the Science Mission Directorate under John Grunsfeld. The science program is helping us find our targets. Through ground-based telescopes and space-based telescopes, we are looking for candidate targets. For option A, these are the single asteroids, the 10-meter class asteroids, which, by the way, are very hard to find. These are real challenges for the observers, but they're up to it, and we've found at least 3 targets. We found 3 targets right now that we've adequately characterized to say that, yes, these are targets we could go to and bring back. And I'll tell you a little bit more about that as well. In addition, once we find a target, we use other assets like our radar here, the JPL operates, to characterize, to understand the spin rate, the size, improve our understanding of the orbit. And that whole program is basically run under the Near Earth Observation Program, which Don Yeomans runs for Lindley Johnson at headquarters. So this is an integral part of the program and helps us identify our targets. By the way, we have targets for our option B as well, which are these larger asteroids, which are much easier to identify. Obviously, we found them, but we need to characterize them as well. We need to understand whether there's boulders on the surface of those bodies. So the redirect mission, there's 2 options we're looking at right now. Option A, again, capture the whole asteroid. Option B, to land on the surface and bring back a boulder. And we're going to make a decision. NASA's going to make a decision on which of these options to pursue around the middle of December. And part of what my team is doing, this cross-agency team is doing, is developing the technical details, working out the issues, understanding the risks, developing our cost story to bring that to NASA in December. And then there is the exploration phase. This is where the crew mission gets involved and actually interacts with the asteroid and brings back material from the asteroid itself. So, how do we conduct this mission? We start with a launch from the Earth, obviously. Our current baseline is that we do a direct injection. We launch directly to the target, or we launch to a gravity assist by the moon. Depends on which target we're looking at. And what I call the Navimagicians, Nathan Strange and his mission designers are just amazing at how they can develop these concepts and run the analysis to show how we actually make these work. So we launch, we fly by the moon or not, and we rendezvous with the asteroid. That process takes on the order of a year. And we're using our solar electric propulsion system, pretty much running it 100% of the time, to rendezvous with the asteroid as quickly as we can. Once there, we will, first of all, rendezvous with it. We have to find it. We have to find it with our optical cameras. Then we approach. We characterize. If it's a small asteroid, we'll characterize it, over a matter of a few weeks maybe. If it's a large asteroid, it's going to take a little bit more time because we really have to map the whole surface and find the targets that we're looking for. Find those 2 to 4 meter class asteroid or boulders on the surface, and then we'll go through the process of actually capturing the asteroid or part of the asteroid, and I'll describe that for you in detail. Once we've done that, then we begin our journey back to Earth, and in fact, with the small asteroids, we're coming with them. The asteroids that we're looking for are ones that naturally will come back to the Earth system in 2023, 2024, 2025, in those time periods. So we're just actually grabbed hold of the asteroid, holding onto the asteroid, and diverting it just enough that it will fly past the moon and pick up a gravity assist and slingshot it into the orbit around the moon. That process from the asteroid back to the Earth-Moon system takes about 2 years, depending again on the mission. The more time we have, the more mass we can bring back, and the bigger the asteroid we can bring back. And then once in the distant retrograde orbit, the 70,000 kilometer orbit, we'll wait for the crew to arrive. And I'll describe all that in a little more detail. So here's the option A. Here's the whole asteroid capture concept. The key to this concept is a capture bag. Now, why would you use a bag to capture an asteroid? Well, the answer is that we know so little about the nature of these bodies. We don't even know how they're held together. We know there's gravity there may be other forces there, but they could be very loose rubble piles, such that when we touch them, they might fall apart. So the logical solution is we need some way to encapsulate, and that's what the bag is about. That bag is about 15 meters in diameter and about 10 meters tall. It would use the better part of this room. the technology behind it is pretty basic. It's actually, we're using a Kapton material for the bag, and we're deploying it using inflatable tubes. And you'll see that in an animation in a second. The whole system, we basically stand off from the asteroid. After we've characterized it, we open our bag, and we fly very slowly, on the order of about 5 centimeters a second, to the point where we basically dock with the asteroid. So let's see if we can run the video. It's a very short video. Uh-oh, there it is. Oh, we lost it. All right, let's see what the guys can go back. We had a little problem with the video before, which is not uncommon. All right, if we can't get it, we'll go on. Hopefully we can, here we go. That's not it. That was the third video. All right. All right, guys, why don't we, let's go on. Give me back control of the screen. Here we go. Let's see, we'll play. There we go. Now you see the petals opening up, just like a flower. You see this is a transparent Kapton material, which we may or may not use exactly that material, but that's the type of low density, low mass, strong material. And now you see us basically flying up to the asteroid. This is, again, much faster than will actually happen. Let's not run that video just yet. And let's see here. Give me back control, please. We can go capture asteroids, but we still have trouble with this stuff. All right. Can we go back? There we go. Here we go. So here is the video finished basically after we had, as we were approaching the asteroid. What we're actually, I like to think of this as docking, because this is a very massive thing. And you know, maybe it's 1,000 tons. Our spacecraft at this point may be still 10 tons. I mean, it's heavier than the Cassini spacecraft. So we basically have to dock with it. And we have to deal with its relative motion relative to the spacecraft. And once we've done that, then we basically are now at a point where we can close the bag around the asteroid. And so the beautiful thing about this inflatable system is we can control how far it's deployed. We can control how it behaves as we want to close it down. And so we basically now are capturing the asteroid, enveloping it in our Kapton bag. And finally, we're finished. We've captured it, and we actually close our petals around it a little bit in order to control it and have it in a good position for us to return to Earth. Now, I want you to think about the fact now that when the crew gets here, the crew is actually going to go between those petals and get access to the asteroid. And you'll see a little bit of that in a future animation. So this is our configuration as we fly back to the Earth-Moon system, and this is what it'll look like as the crew approaches it. We have a test bed up on the hill here at JPL. We've built a 1/5 scale, so we're talking about a 3-meter diameter by over 2 meters tall system in which we can have all the basic elements. Many of them are flight-like. The Kapton bag is the real thing. And we can demonstrate and work with these soft goods, which is, when those of us that have worked on airbags and parachutes and whatnot realize this is something you have to do by hand. And so we built this to work with, to understand. And what the capability we've also built into the system is the ability to during the capture process, measure the forces associated with the relative motion of the asteroid body with our spacecraft. We want to understand what happens as a rotating asteroid inside the bag makes contact as we close on it. So this is a capability that measures the forces, and we can do closed-loop simulation of that whole system. So it's a beautiful way to understand exactly how this system is going to perform. And when we go to flight, as we start to build up for flight, this is a system we can test fully here on Earth in 1G. That system deploys in 1 gravity. We'll make a system that can do that. We'll be able to fully evaluate, test, and evaluate performance of the whole system right here on Earth, right here, hopefully at JPL. So that's option A. So here's option B, pick up a boulder. This is a much more challenging job, actually. This is technically a very challenging job because we're landing. We're taking a whole 10-ton spacecraft and landing it on a rotating asteroid that we know very little about. We'll know where the boulders are, but we'll not know a lot more about the nature of the asteroid, its surface, for example. Then we won't know a lot until we actually touch it. So our strategy is to use 3 landing legs. They're about 5 meters long, and a pair of 7 degree of freedom robotic arms with special end effector to grab the asteroid. Those arms are about 2 meters, well, they're at least 2 meters or more long, very much like our MSL arms. And those legs are specially designed to control the landing and also to push up. But the part of what makes this challenging is we've got these big solar arrays, and I'll show you how big they are in a minute. They're part of the spacecraft. So this is a very, very interesting, challenging problem. But one of the nice things about working with asteroids versus like the surface of Mars, gravity is very low. We're talking about micro-g of gravity. So instead of the 7 minutes of terror, this will be the 7 hours of terror. You know, so we've got a lot more time because things will happen slowly. So let's see if we can run the video, John. Be patient. Okay, good. We're going to back out to Windows here. I don't even see it up there. Oop.
Have you chosen an operating system for the spacecraft yet?
Yes, it would probably be VxWorks, which is what we're running on 750 today. So the avionics, I'll talk about the spacecraft in a second, but the avionics and the software would be derived heavily from JPL Heritage with our current implementation. So let's see what John's up to. If I say I'm ready to give up, I'm sure it'll work. All right, why don't we go? Oh, there we go. See? Okay, so you didn't quite see it from the beginning. I don't know if we can play it and replay it. But we'll go through it, and if we can replay it, that'd be great. I know that's asking a lot. Okay, there. Now you see it landing. Again, this is much faster than would actually happen. The legs absorb the energy. You see the 2 robotic arms coming down with microspine grippers. They're grabbing the asteroid or the boulder, and then the legs push us off. And then we nestle the boulder into the surface of the spacecraft, and then we close the the landing legs around it and hold it for the crewed phase. So, but you can see these solar arrays. That wingspan of those solar arrays is 35 meters. This is a very big spacecraft. Okay, now can we stop it? Thank you, John. All right, let's see if we can get back. We'll make this work better tomorrow night. So they're probably trying to, okay, here we go. So as in the case of option A, we've got some great testbed work going on out at Goddard and at Langley. These are a couple of pictures of the test setup for those landing legs that's going on at Langley Research Center. I've got a big air-bearing floor. You've got these large, I think on the order of 5 meter long arms. And starting tomorrow, we're actually demonstrating the capability of these arms to operate in a coordinated fashion, to simulate the landing. We'll be eventually simulating the actual capture of the asteroid. So this is, again, a great multi-center effort. That's another thing that makes it unique. We're funded by multiple directorates. It's actually the work of multiple centers to accomplish a mission like this. Let me talk a little bit about solar electric propulsion. I know there's a number of people in the audience here who have some more than a working familiarity with that, but this is enabling for the Asteroid Redirect mission, and it's now recognized as enabling for these other missions that we want to do in the human exploration program. As I said, we're talking about a 50 kilowatt system here that takes 40 kilowatts of that power and turns it in and uses that to propel, to accelerate xenon atoms, xenon is our propellant, to about 30 kilometers a second. This is an extremely efficient system, but the force we're talking about is only about 1.5 newtons. It's a very low force, but it's a very efficient system. So it takes a long time, like I said, a couple of years to apply enough delta V to move that asteroid. And the amount of delta V is only about 150 to 200 meters per second. That's how much change we're able to do over 2 years, but that's just enough to get the asteroid to fly by the moon and get into orbit. So there you see one of the engines as they exist up in the test lab here at JPL and also testing at Glenn. And one of the key things is that solar array. That solar array, you know, big solar arrays exist, but they don't exist at this high efficiency. These are 30% efficient cells on a blanket. It's not a rigid solar array. So the specific power of these arrays is quite a bit higher than anything that's flying today, by at least on the order of about 50%. And it's scalable. It's scalable up from this 50 to 100 to 150, maybe even to 200 and beyond. So that's a big part of what we're doing is this extensible? Is what we're doing extensible to these future applications? Here's what the spacecraft configurations look like, option A on the left and option B on the right. You can see these are big machines. They're bigger, quite a bit bigger than Cassini. And of course, big part is we're carrying 10 tons of propellant in very long tanks. This 10-ton system is got to be scalable itself. We want it to scalable up to 16 tons. That's the kind of propellant load we think we need to go to move big cargo to Mars. Another thing I want to point out is the modularity. Because this is being developed across the agency, we needed a design that was modular, that we could imagine working on in different organizations with clean interfaces. And so we've got the SEP module, which is the responsibility of Glenn Research Center, the mission module, which is JPL's responsibility, and the capture system. So for option A, that responsibility is JPL. For option B, that responsibility is Goddard and Langley. So again, you know, these are massive machines, but because of these clean interfaces, we think we can develop them in a very efficient way. So here are those big solar arrays I talked about. The Megaflex from ATK, 35-meter wingspan. The ROSA from Deployable Space Systems, 51 meters. These are big solar arrays. So part of the challenge for our guidance and control team is how do we control these big flexible systems when we're grabbing hold of an asteroid and when we're landing on the surface of an asteroid. Very interesting, challenging problem. Luckily, again, because gravity's low, things don't happen real fast. And we think we've got a pretty good strategy for controlling these systems. I want to talk a little bit about planetary defense. You probably recognize those images up above. The one, of course, is the dinosaur killer, the 65 million year ago impact of a very large kilometer-class asteroid, which was a planet killer, is the way we refer to it. And there, over there on the right, is an example of maybe the asteroid that came in over Tunguska in Siberia, or the smaller one, the 17-meter one over Chelyabinsk. So those are the hazards that asteroids represent. And if there was a big one coming at us, you know, hundreds of meters or bigger, we'd need to do something about it. Well, there's various techniques, kinetic and nuclear, but we have, with the ARRM system, the capability to do what we call these gradual but precise changes in velocity. And there's a couple of techniques that ARRM can directly demonstrate. So for option B, we can demonstrate the gravity tractor, or what we call enhanced gravity tractor. And the way the gravity tractor works is it's the gravity force between the big body and the little body that represents like a string that holds the two bodies together. And then we use our thruster, which is this very light, you know, this very low force thruster, to just pull basically the asteroid and give it some small delta V. It's a very small change in velocity. For what we could do on a couple 100-meter object, it's a few hundredths of a millimeter per second over about 60 days. But that's enough that our deep space network can measure that change in velocity and would give us some evidence that we'd actually accomplish that. I don't feel we necessarily have to actually demonstrate the measurement, but we know how to do it. The other approach, which is a unique one, is called ion beam deflection, where we take our thrusters and we basically turn the spacecraft back end toward the asteroid, and we start firing our engines. Now, that basically has the effect of billions and billions of xenon atoms impacting the asteroid surface and providing the change in momentum to change its velocity. So that is also a technique that we can demonstrate. And on a small asteroid, we can change its velocity like a millimeter per second, which is very easily measured by the Deep Space Network, in just an hour. So we've got techniques that we can show and demonstrate and have confidence that we understand the basic principles. But if we were faced with a real target, again, these would be augmentations to probably what would need to be a much more serious capability associated with a kinetic device. Okay, so I'm coming to the end here of my talk. I'm going to talk a little bit about the crewed mission. Here you see the crew launching on the Space Launch System on Orion, and hopefully you'll be tuning into the test launch of the Orion on Delta IV, or on Atlas, I guess, on December 4th. First flight of the new human-carrying capsule. There will be no crew aboard. Do a few orbits around the Earth and re-enter. Then you see the Orion and its service module on its way from Earth toward the Moon, rendezvousing with the ARRM robotic spacecraft, and then the crew egressing from the Orion and sampling the asteroid. The crewed mission involves actually 2 EVAs. We believe we've got the capability for 2 4-hour EVAs that can accomplish this. And then the Orion leaves Earth or lunar orbit, comes back to Earth, re-enters the Earth's atmosphere, and parachutes safely to the water, as was done on Apollo. So we have one more video to do. Let's see how we do. Now, I'm going to narrate this. I've got a great soundtrack that goes with it called Born to be Wild. Unfortunately, I don't have the rights to use it. But it really goes well with, you can hum along, we can all hum along. It really goes well with this video. So, I guess while they're doing that, I will show you, this is the bag material. This is about all we think we need. This is Kapton plastic, which is something we use to make all of our thermal blankets. Here's it reinforced. Okay, here is, okay, so that's the target. That's the ARRM spacecraft in orbit at the distant retrograde orbit. And now here you see Orion launching, so here's the words, get out on the highway. Looking for adventure, you know. Yeah, here we go. So here's the crew. It's a 2-man crew. That's the capability right now that we have with the first generation of the Space Launch System to inject to the Moon. Here we're leaving Earth orbit. And the human spacecraft will do a close flyby of the Moon and do, again, a gravity assist, which is something we've never done with crewed spacecraft before. Again, an expertise that JPL has developed and is the world's best in. So now the crew is arriving in the distant retrograde orbit, and they're rendezvousing with our spacecraft, which is sitting there waiting for it. The crew will use a set of instrumentation to dock. We have a docking ring on the spacecraft. Same instruments that the Orion will use to dock with us are the same instruments that we used to dock with our asteroid and to control the landing for option B. Again, this is a first. I mean, this is a robotic spacecraft built by people who build robotic spacecraft working directly with the human human spacecraft, first of a kind. And it won't be the last. This is really part of the way we're going to need to do business if we're going to go out and explore the solar system and beyond. So you see the crew now with handholds that are on our spacecraft. We've actually demonstrated in the neutral buoyancy lab at JSC the operations you're seeing here. Crew have actually, with the spacesuits they would likely fly, at least the current ones that we're thinking of flying, we've demonstrated the egress from Orion, the movement along the spacecraft, actually opening up the bag and taking samples. We've proven all that out because we wanted to understand with this spacesuit, which isn't necessarily our favorite choice for a spacesuit, but one that meets other constraints, that we can actually use that spacesuit to get to the asteroid and get material. So again, we've proven kind of the initial end-to-end concept of how that would be done. So samples and return. I didn't point out that this mission is a technology demonstration mission. This is not a science mission. There will be great science that will come from it, just like in Apollo. Apollo was not a technology, or was not a science mission. But the understanding of the asteroid, or the whole asteroid, or understanding of the part of the asteroid will be a wonderful opportunity for science. And here you see Orion landing. And when in fact Orion, the test unit, lands, it will be right off the coast here of California. Okay, we got all 3 videos done. All right, almost done here. So what I want to do, so I want to talk just real briefly about how we're going to go implement this project. We've been in a couple of years in this conceptual phase. We're going to make a decision about which mission we're going to go do, and then we're going to go through a mission concept review in February, where we basically hope to get permission to start the project. We'd have about 16 months of formulation, then we'd go into a 3-year development. Those of us here that work on projects, understand 3 years is kind of aggressive these days. But part of what this mission's about is helping change the way we do business in NASA, in the human program and in the robotic program. So we're approaching this in an innovative way, what we call lean implementation. We're going to be very creative about how we do this job. And we've got good support at the highest levels of the agency to kind of pathfind this way of doing business. This current schedule has us launching as early as June of 2019. We haven't got official approval from the Office of Management and Budget or the Congress yet. We're hoping to see evidence of that as we go through the year. So the likelihood that we'll hold to this schedule is not very high. But nevertheless, the approach we're taking, this innovative approach in what we do and how we do it, is really central to the importance of this mission. I'm going to finish with this very brief, again, a return to the fundamental applications of the ARRM missions, the robotic and the crewed mission, to both future human exploration mission, but also future science missions. And the ability to move large payload around the solar system, the ability to use innovative sensors and sensor technologies to do efficient proximity operations, to land and interact on the surface of natural bodies, low-G bodies, the design of missions for low thrust and maybe combination of low thrust and chemical high thrust, which was really the underlying principle behind that first picture I showed you. Then long duration and high power solar electric propulsion, and finally, further engagement of extravehicular activity in challenging environments. So with that, I'm going to leave you with this beautiful collage of ARRM, the Moon, and Earth, and open it up to any questions. Yes, sir.
Quick question. For the longer range goals, are there any plans for resource extraction, fuel feedstock extraction from bodies for
Yep.
the Mars leg of things?
Yeah, well, there absolutely there's a number of potential applications for this. And we are talking to organizations like Deep Space Industries and Planetary Resources about how they would take advantage of what we're doing. So they could take advantage of the materials that we actually bring back, in maybe even, in the time of our mission or in some subsequent mission. So, if we can bring back some carbonaceous chondrite with hydrated minerals, might be a great source for water. But we know these will be great sources for oxygen. So there's a lot going on there. And I think, so we're going to include that in our planning.
And second half is for the Rosetta team, how much coordination is there on what they are in the process of learning?
We're not coordinating with Rosetta. We're looking at what OSIRIS-REx is doing and trying to make sure we understand what's going on there. But both, in the case of both Rosetta and OSIRIS-REx, there's a lot of ground in the loop. For our mission, we're going to go much more on the autonomous side. So we're going to learn from both of those missions about the nature of the bodies that they're visiting. And as a matter of fact, Bennu, which is OSIRIS-REx target, is a potential target for us. We could go there and bring back a boulder from Bennu. So yeah, there's a lot of things to be learned from all these missions, and we're sharing information as we go. Thank you. Yes, sir.
I have two questions about Plan B.
Mm-hmm.
So the first one is looked like I can see the difficulty of having a bag, and there's no bag in your image for Plan B.
Not at this point.
And,
there could be.
And so my concern is that the thing you think is a boulder is just kind of a blob that kind of dissolves when you start to handle it.
Yep.
And so the other part of my question is how you mentioned you had some way of characterizing these large asteroids as having boulders, and so could you say a little bit more about that?
Well, we have got basically three targets we're looking at for option B. One is Itokawa, which Hayabusa went to, which we have very good imaging of. So that's a well-characterized body. And we believe there are a number of boulders on that surface that are accessible to us and can be extracted. But the point you bring out about the nature of actually the boulder itself, what's the integrity of the boulder? How well is it attached to the surface? How much of a cohesive force is there? Those are all issues we're absolutely aware of, we're thinking of, but we won't know for sure until we get there. So that's not uncommon for us. We're going to land on Mars somewhere. We won't know what it's like until we actually get there. So we need to design our systems to be tolerant of that. And that's a big part of what we're thinking about. But that's one of the things that adds to the complexity of option B. But at the same time, on option A, the targets we have today, we have a pretty good understanding of the size. We have a range, like 4 to 7 meters or something like that. But we don't know the mass in absolute terms very well. Only one of our targets do we have a pretty good upper bound on mass. So that's another inherent uncertainty associated with this kind of exploration.
Thank you.
Well, I see this as rather fascinating to put an asteroid around the moon. And we spent a lot of money on all these missions from, Mars but I have this question that's never been answered adequately.
Uh-oh.
Why in the heck haven't we set up a space station on the moon?
Aha.
Why?
Okay.
What's going on? There's some kind of a mystery, and you cannot give me an adequate answer. I know that.
Okay. Well, I was the chief engineer of the Constellation program, and part of what the Constellation programs, one of the first things we were going to do was establish habitats on the surface of the moon that would allow us to prove out the systems that would need to work for weeks to months to years in the hazardous environment of the surface of Mars. So that's where we were going with that particular program. Unfortunately, that program got canceled. So there's still a need to prove out long duration, high reliability systems, habitats with an environmental life support system that can operate for years and can easily repair to. That's part of what we need to go prove out. Now, why we're not doing that today, you need to go talk to friends in Congress. or in the White House.
Okay.
But that's not NASA was moving in that direction, but we were directed elsewhere.
To talk to the politicians and to talk to elsewhere besides the scientists is a better answer.
Well,
Thank you.
Yes. Yes. Unfortunately, scientists don't control the money as much as we wish we did. Yes, sir.
First, what's the relationship between the ecliptic and the orbit plane of the distant retrograde orbit?
They're pretty close to the same. We're pretty much flying in the plane of the ecliptic. We can fly with quite a range of declination with that DRO.
Yeah, that makes it a bit easier for the astronauts to get there than if
Yep.
they got to change the orbit plane.
Yeah, we've looked very carefully at what it takes for the astronauts, the crew to get there.
Now, how much of your propellant budget can you afford to dump the angular momentum that's going to be inherent in any rotating asteroid?
Very good. You'd be a little surprised at this, but we've looked at that very closely, and you'd be surprised at how little it takes. When the way the asteroid we're talking about, let's imagine the worst case scenario right now is we're assuming the asteroid is rotating at about half an RPM. So it's not very fast, but this is a big object. So once we grab hold of it, all of our analysis shows what's going to happen is we're going to go from spinning like this to spinning like this. We'll go into a flat spin. And in a flat spin then, I can turn on my thrusters, my hydrazine thrusters, with a big moment arm. In a matter of hours or a day or two, I can despin that asteroid. And that's exactly what we need to do before we start our maneuver back to the moon.
We'd be using hydrazine.
Just
not
hydrazine
xenon.
thrusters, 22 Newton hydrazine thrusters.
And the third is more of a comment than a question. You can get a lot more electric power per kilogram and per cubic meter with the space nuclear auxiliary power systems that were developed in the 70s than you can with solar panels. And he plans to do that for very heavy, you're talking about, you're talking about 10 tons, you're talking about 100-ton spacecraft. You're going to need something that can't possibly be powered by solar power.
Well, again, I'm not sure exactly what nuclear system you're talking about. But
It's the snap reactor from the 70s.
oh, no, those are very low power. You can't, the
They're 100
RTGs we flew here on Cassini were, 100-watt class.
No, the snap was 100 kilowatts.
The snap, okay.
Yeah, space
Okay.
nuclear auxiliary power. It was a reactor, not an RTG.
Okay, a reactor, because I'm thinking of the smaller ones.
100
Yeah,
kilowatts.
someday, reactors may play a big role in thermonuclear propulsion.
Yeah.
Yeah, but we don't need that today. We believe we can get up, just like we're doing at Jupiter now. We're flying Juno to Jupiter with solar arrays. Rosetta was out to 5 AU with solar arrays. We can do that.
Yeah.
And we believe we can.
Nothing very much bigger.
Huh?
Nothing very much bigger than those.
No, yeah, it's we're not going to go to Saturn with solar arrays. I don't think, but we believe we can assemble multi-100-watt solar array configurations that can fly between the Earth and the Moon, and Earth and Mars. Yes, ma'am.
Hi. Are there any plans to add any additional ion thrusters to the robotical spacecraft to increase velocity?
Yes, there is. We are looking today at upping our power, say from 50 kilowatts to 60 to 80. And as we go up in power, basically each of our thrusters is about a 12.5 kilowatt thruster. So if we want more power, if we want to be able to move more mass faster, then we would add a thruster. And so we just kind of would grow in increments of like 12 kilowatts. So if you think of like a 150 kilowatt system, it's 3 times our system. So what we would nominally do is take our 3 thrusters, turn them into 9, and probably put a spare or 2 on them. And that gives us the higher power and the higher thrust capability of our systems. On the other hand, maybe you're thinking, we could certainly go to higher power individual thrusters. We can go from the 12.5 kilowatt to multiples of that too. But again, that's stuff that needs to be proven. One of the things we have to prove with our solar electric thrusters is how do you prove that you can operate a thruster at the power levels we have and push that much propellant through it? The ion thrusters of Dawn are basically pushing 150 or so kilograms per thruster. We'll be pushing 3 tons, 3,000 kilograms per thruster. So that's part of the art and part of the challenge of our solar electric propulsion experts here at JPL and at Glenn to prove that out.
Thank you.
Two questions. One, with your landing and boulder pickup plan, did I understand correctly that you're planning to store energy like kinetically in the legs? Is that
Not
these
really store
springs?
it. No, you
Okay.
won't store it. You'll use you've got actuators in the legs, 4 actuators per leg that basically will allow you to to land gently and conform to the surface. And then when you're ready to take off, you just go from that spring point and you turn the actuators on and straighten them out.
Okay, and second question, with your bag strategy, or I suppose both of them really, since you don't know the composition of the asteroid, you're not going to know the center of mass ahead of time
Correct.
or any of that. So
Exactly right.
So how do you articulate the payload or the engines or?
Well, that's absolutely one of our challenges. We don't know the shape, for example. That's one of the things we're going to have to figure out how to deal with when we actually get there. And we'll develop a model. We'll know where the spin axis is, the rotation axis. We'll know the CG is there. But depending on where it is, we'll need to be able to accommodate that. So one of the studies we've done to date and will continue to do is look at different configurations, different shapes, different mass properties, run some Monte Carlo analyses, and look kind of probabilistically, do we have a system that can deal with the 99% probable scenario? Now, with those pedals, we have the ability to move the body around once it's inside, once the asteroid's inside, and once it's touched on the surface of the spacecraft, on the top of the spacecraft. So we're going to have to do some clever thinking when we actually get there, decide what we're going to do, and that's the same will be true with option B.
Thank you.
So the Constellation program was canceled. I think that's because of budget. How would you say we would go about going to Mars if NASA had an ideal budget as opposed to what it is now?
Well, there's a number of people that have been looking at human exploration architectures for the moon. There was what we call the DRA-5, which was basically a design reference architecture for human exploration. And it involved a lot of chemical propulsion, a lot of rocket launches and things like that. So we're looking at architectures today that involve a lot more of these SEP systems, which are much more reusable, we believe, than the other systems. So I haven't heard any new numbers on what such a program would cost, but what we're talking about today is what we call a sustainable exploration strategy, something that builds on, that tries to work within the budget we have today, that builds on the robotic and the human program capabilities, sharing those like ARRM is doing, builds on the technology developments, builds on commercial capabilities, and is going to involve international partnerships. So all of that is a real challenge to put together a program that actually can be accomplished. It fits within the kind of constraints we can imagine. So it's a great dream a lot of us have. I don't know what the real, if somebody could write a check today, I don't know exactly what it would cost, but it's in the tens of billions.
Thank you.
Hi.
Hi.
You mentioned during the landing phase of option B that you had some ideas how to, preserve the integrity of the solar panels. Mm-hmm. And I was just wondering if you want to explain what some of those ideas are in a little more detail.
Sure. Well, again, depending on where you're landing, you've got to have if you imagine that 50-meter wingspan, you've got to have clear access for those. You'll obviously rotate those solar arrays away from the surface. The solar arrays themselves are very flexible. They're going to be a 1/10 of a hertz system. So we've got to deal with that. We need a system that's recognizing and is controlling all of that activity while we land very gently so we don't excite anything. So that's a control design problem that we know how to handle. One of the things we don't yet understand and how we're trying to characterize is the potential for dust or for debris during any of our interactions. That as we pull the boulder up, we're going to pull some material with us. Well, what happens to that material? Are we at some risk of that? And that's one of the ideas. We do have some concepts where we could use a bag to encapsulate the boulder for option B. If we were going to Phobos, for example, bringing back a sample from there, for planetary protection purposes, we might need to encapsulate. So those are options that we may look at in the future. But trying to We won't, again, we will not know until we get there what we're really facing in terms of finding a safe boulder to pick up and a safe place to do it, except on Itokawa. We think we can do that on Itokawa today.
Do your studies so far tend to favor one design versus the other in terms of the
Well,
array of the solar panel?
my job is to be completely objective about that. There's members of my team that are pretty pro one or the other. So our job is to bring forward to the decision makers, Robert Lightfoot, our associate administrator being the principal decision maker here, a balanced story. You know, what are the costs? What are the risks? What are the cost risks? You know, what are the benefits of one versus another from different communities? So I can't tell you what they're going to make that decision based on. And I can tell you, though, that I would be extremely happy, and I think we as an institution, JPL, would love to do either one of these options. I think they're both the kind of challenging, exciting kind of mission that this institution is just designed to go do.
Thanks very much.
Uh-oh, we got questions from the internet here. Oh, when is a demonstration mission to test ARRM scheduled to be flown? A demonstration mission? Well, there is no demonstration mission to test ARRM. ARRM is a demonstration mission. It's a technology demonstration mission. So we don't feel that we need any precursors per se to prove out the spacecraft. It's great to have precursors of the targets. So for example, you know, when OSIRIS-REx is at Bennu, it's going to tell us a lot about that object and whether we've got boulders that we can go to. But we won't know that until about 2018. Okay, how do you calculate the flight path away from an asteroid with a variable unknown mass in option B? Well, it turns out option B is fundamentally different than option A. Option A, because it's so massive, you know, hundreds of tons, we're going with it. It is, you know, we've docked to it and we're just nudging it a little bit. With option B, when we're talking about 10 tons, maybe 20 tons, you know, that's not much more than the propellant we're carrying on board. So we're actually able to fly that mission to where we want. So we can control the velocity. We can put a lot more delta V into that. The difference, though, between A and B is another big difference is the asteroids that are the small asteroids are coming back into cislunar space. Their relative velocity to Earth, their V infinity, is small. It's 1.5 to 2 kilometers a second. The big asteroids are moving much faster. So we've got to provide a lot more delta V to bring back the boulder from the big asteroids. So our navigicians here know exactly how to do these calculations. And so we basically can deal with the variable mass, but there's a limit to what we can bring back in a certain period of time. So if we find out we picked up too big a massive boulder, we want to get back at a certain time, we may have to put it down, drop it, and go pick up something else that maybe is a little less massive. On the other hand, we can also just take a little bit more time, assuming we have enough propellant. Okay, got 2 more questions here. Will the samples be contaminated by the capture process? Very good question. The reality is yes, to some extent. You know, in the bag, you know, the bag itself may represent some level of contamination. Again, this isn't a science mission per se. We're going to be very sensitive to what the science community would like to do, but we'll find ways to try to minimize that effect. But there's a big difference here because you've got a whole body. You can scrape off some of the surface and get inside it if that's what you're interested in. So there is the chance on option B that you can contaminate with xenon or even hydrazine. With option A, you know, you're inside the bag, you're maybe a little less likely to be contaminated. So we'll see. And again, it's going to depend on what the science community would like us to try to do. Potential value are there in having this asteroid available to the potential value. Okay, why are we doing this mission? Okay, well, as far as, you know, I already told you all about the spacecraft itself, but having asteroid material available to us. I mentioned, one of you asked about, you know, the idea of using that material for commercial purposes. You know, there are companies that would love to find a way to turn asteroid material into useful things like propellant. And so we are bringing samples, large quantities of material back that they can look at how to process. In fact, could even process parts of the asteroid that we brought back. If you think of the planetary defense problem, knowing how an asteroid is held together, knowing what the inner structure of an asteroid is, would be of enormous value. Again, from a science point of view, there's a lot of opportunities for science. And again, I think because this is a technology demonstration and it's about human exploration, it really is about how do we develop and operate for the first time in deep space with humans. So with that, I'd like to bid you a fond evening and thank you very much for coming.